This is going to be a primer on Mathematica. It's a symbolic programming language. Also, in recent years, it's been called Wolfram, the Wolfram language. So, as for the scope of this will not go through basic concepts that are typically covered in most programming introductory courses. The assumption will be that you are familiar with some other language, C, Java, Python, whatever it is, MATLAB perhaps, and you grasp basic programming concepts like variables, values, control flow, for loops, while loops, so on and so forth. The focus will be on the essence of what the Wolfram language is deep down and what makes it different from your run-of-the-mill imperative languages. Hopefully this will convince you why it is an elegant and most of all fun language to learn and use. What is a language really? Well, according to SICP, the structure and interpretation of computer programs, this is a really famous textbook and a beautiful and elegant one too. I highly recommend everyone who's interested in programming to read it. So according to that text, a language is really built up or constituted from three main items: primitives, means of combination, and means of abstraction. Primitives are essentially the building blocks of the language. They are kind of like axioms from mathematics, things that are to be taken for granted, sort of black boxes, elements that cannot be subdivided into components. They are the most elemental part of the language, and everything else in the language is built out of those primitives. They could be data like numbers or strings, or they could be procedures, elemental procedures that are just given to us, and they just work without us even having to worry about how they are implemented. The means of combination are simply the means by which those primitives can be combined together to form compound or complex structures that essentially might describe computation or might be a build-up of a more complex data structure. For example, building a list of numbers from numbers, right? So it is at the heart of the language, the syntax required to combine primitives together into something that is constituted of primitives that describes something, either a process or a procedure or a compound piece of data. The means of abstraction are the means of taking this compound object that we created out of combining primitives, and then encapsulating it in a way and abstracting it in a way such that we can use it as if it was a primitive. This, of course, reduces our cognitive load. We no longer need to think about the internals of this compound object. We just use it as is. Imagine someone writes a library for you and you want to use it. You would rather not keep thinking about how it was implemented. You would just want to use it as if it was part of your language from the get-go. A good language is a language that provides clear syntax and well thought out mechanism to achieve such a thing. And I do believe this third item, is the most important differentiating aspect of any language. But also there's another perspective from which to look at things. A language is not merely its lexicon or syntax, that is the arrangement of keywords and elements allowed by some standard or grammar, but it is also defined by the interaction of a program written in it with an interpreter or evaluator. So it's not as simple as taking the body text of a program and trying to understand language from that perspective. There is something interactive happening here. A language is being interpreted. It sounds obvious, but this is the appropriate way of looking at things. So it's a yin and yang situation. Essentially, the evaluator interprets the code, provides the environment that affects its execution, and holds all the primitives for it. The program's text steers the evaluator and configures it as required within the degrees of freedom allowed. It is very much a two-way street, and defining a language properly requires both syntax and evaluator behavior, or essentially semantics. There is another layer to this. Before code is even passed through an evaluator, it might go through multiple transformation cycles. This is what a macro system is. The most prominent example being the powerful macro systems of the Lisps. You might be only familiar with the C microsystem, which is a rudimentary and not very powerful form of the concept. This is generally called metaprogramming. That is programs that generate programs that then are evaluated. It is definitely not a trivial undertaking, and with its power comes the risk of making code hard to follow and debug, but it has its place. However, Mathematica models the distinction between transformation and evaluation because at its core, it is a term rewrite system, an altogether different beast. Think of it as a mixture of both code transformation and evaluation, with all the advantages and disadvantages of both. So far, I have been emphasizing evaluation. That is, the objective of code is to be evaluated into some sort of result. But in some cases, it could be the side effects of the evaluation that are the desired outcome, like something printing on screen, for example, or saved to disk, or a musical note played, or graphics displayed, all valid objectives for a program. Also, during evaluation, some internal state of the environment the program is running in might be changed by it in a way that affects code evaluation down the line. For example, changing the value of a variable. This phenomena is called state mutation. There has been an idealist push against side effects and mutations as undesirable, something that you want to, if not eliminate completely, try to minimize to the absolute minimum. Right, so this happens mainly with the functional paradigm of programming. This is a paradigm where side effects and mutation are eliminated and only pure functions are allowed. What do I mean by pure functions? There are objects where the output or their output will forever be the same for the same input whenever the function is called. Truth be told, Mathematica is at its most elegant and powerful and most comprehensible when we try to adhere to those functional paradigm principle, right? So it is designed and optimized for that style. It can be programmed in other styles, of course. It is a general purpose language after all and supports multiple paradigms, but that should be minimized. I say minimized and not eliminated because side effects and state mutation do have their place and are even needed under some conditions. Anyway, this is a deep topic that I might go and do videos about later, but for now, let us jump into Mathematica itself. Well, what are the primitives of Mathematica? Well, those are primitives that you would find commonly in many languages. They are run-of-the-mill primitives, nothing fancy. I would say they are closest to the kind of primitives that you'd find in Lisp, but they are also shared with most languages. There are, of course, the numbers. Mathematica implements a full numerical tower. For example, 1 is a number. So if in the evaluator input, if I type 1 and then do Shift Enter to have it pass through the evaluator, it will just return the number itself, nothing fancy. 13, right? It returns the number itself. It understands rational numbers. So if I do 3 Control/4, I get 3/4, which it understands as a rational number rather than a decimal number. It can, of course, do decimal numbers. Let's say 3.14, Shift Enter. So it understands that too. It also has big numbers. I mean by that is that you can represent integers that are way beyond what is the machine by itself capable of representing. So there is software understanding of those big numbers. For example, let's do 10 factorial. That's a huge number. Let's do, I don't want to put something that's going to be, not fill the screen. 50 factorial is also another big number. So this sort of integer will never fit in a machine register, yet Mathematica has an understanding of it as a primitive. Let me try something else. Let me try 100 factorial. This is going to be a ridiculously big number, and so on and so forth. So this is like a full, what's called a full numerical tower implementation. By the way, this is what's called the notebook interface, something that Mathematica pioneered. Well, there really was maybe one example of it at the time, but the first time it was introduced into a big commercial product was with Mathematica. Now there's an open source alternative called Jupyter that works with Python and other programming languages. And I do believe it has a kernel for the Wolfram language, but I'm not sure. I haven't tried it. But the idea is that in a cell, you provide an input, you do shift enter, and then you get an output cell. And that's how you do your calculations. And you can mix, the idea is that you can mix text with formatting along with programs that you evaluate, and then you show the result in the same document. So this is what's called the notebook approach to testing code. The key thing to observe here is that primitives essentially evaluate to themselves. The other kind of primitive is a string. String is just a collection of characters between quotation marks. So I could, if I go into an input cell and just type in the quick brown fox, shift enter, it just, again, primitives evaluate to themselves. So it just prints out whatever I spits out whatever I gave it as a string. That by itself, shift enter. Oh, so if I type in something and just in a cell and type enter, just press insert enter, nothing will happen because I just go to the other line to input the other line of my program. So I could have a multiple line program. However, if I want to evaluate, I just do shift enter, right, to evaluate what I've just typed in. So those are strings, pretty basic. The third kind of primitive that I want to discuss is symbols. Symbols are essentially just like variables. They are any string of characters, but they're not strings, so they don't have quotation marks. So if I type in X and press shift enter, I get back an X. Symbols also evaluate to themselves like everything else. If I put in Y, I get Y. If I put in F, I get F. Foo, it auto-completed to something. If I put in foo and type in shift enter, I get foo. Bar. Right. Notice that Mathematica, when I type something, it tries to give me suggestions. So I want to ignore that. But this is what symbols are. They are essentially primitives that return themselves. What is their point? Well, their point is not themselves per se. Their point is that you can bind them to something. You can set them so that they point to another primitive. So that they stand in for another primitive. They could stand in for a number. So I could point X, for example, to the number 3. So I'm going to explain this notation later. There's more to this than just an equal sign, right? And then I do shift enter and it evaluates to 3, but now if I type in X, I get back 3, right? X now is forever until, well, not forever, it's until I clear it or I restart the MATLAB session, it's gonna be 3. So let's say I type in Y, I get Y. I type in X, I get 3. All right. So this is what symbols are. There's a bit of subtlety to them that I'm going to explain as we move along, but essentially that's what they are. They are represented by a bunch of characters strung together without quotation marks, and they can point to something. They can bind to something else, some other primitive, or they could bind to some more complicated object. They could bind to a container that contains many primitives, right? Or they could bound to a program. You can set a program to be equal to a symbol, so that when you type in that symbol, you invoke the whole program. So there's more to be said about them, but that's what they are in a nutshell. By the way, all those primitives that I've talked about, in jargon, they are called atoms. So we say those are atomic elements. Okay, now let's move to the means of combination. In Mathematica's case, all primitives or atoms are combined together in what are called M expressions. Atomic primitives are considered valid M expressions, by the way. That is, any number, string, or symbol by itself is an M expression. That is because the definition is recursive. M expressions have the following form, where k could be any integer, and each ei is either an atom or an M expression. Also, E1 is called the head of the expression. Okay, let's do some examples of M expressions. For example, we could do foo, that's the head of the expression, and then I do the brackets, and let me put in x, comma, y, comma, bar, again brackets, z, w, and then press shift enter, and the thing evaluates to itself. All symbols that are not known to Mathematica, were not bound to anything, just evaluate to themselves. No error is thrown. But this is a valid M expression, right? It doesn't mean anything right now. It's just how valid Mathematica syntax looks like. Mathematica will not throw an error for this. There's one interesting thing we can do. We could try to see this expression in a different form. So there is a symbol in Mathematica called 3-form that has a meaning. And I'll explain later what does it mean when I say a symbol has a meaning. But we can take this expression that we defined or that we typed in, and we can put it inside 3-form. And then the evaluator, when it sees 3-form, it does this. It takes this M expression and it displays it in a 3-form. It essentially displays the head first, and then displays what are called the arguments of the head, or what are inside the brackets. So 3, y, and bar. And then bar is another, remember the recursive definition, bar is another M expression bar is the head of another M expression, and it has arguments z and w. So 3-form is a really useful symbol or function to use to sort of show M expressions graphically in this way, which might be sometimes easier to read and understand, right? However, you write them in, you type them into Mathematica this way. Let's do another example. This time I'll make it a little bit more suggestive. Let's do times. And times, by the way, is a symbol that's already defined by Mathematica. It's defined in what's called the global rule base. But I want to bypass anything that Mathematica defines. I want to do my own M expression. So I'm gonna just put in the number 2. So now it's blue. That means it's not recognized. But anyway, nevertheless, it's a valid symbol and it's a valid hit for an M expression. And then let me see what do I want to put here. Let's say I put 4 and then I put plus. Again, I don't want to use the plus defined by Mathematica. Let me put plus 2. and then put in 3, 4. So this evaluates 2 times 2, 4, and then plus 2, 3, 4. Okay. So now, and we can also do tree form of that expression, that M expression. Oh, I made a mistake somewhere. Oh, capital F, okay. Mathematica is case sensitive, right? So this is another example of an M expression. Now what happens if I use symbols that are known to Mathematica? Instead of times 2, I plug in times. Instead of plus 2, I plug in plus. What will happen here is that Mathematica is going to recognize those heads, times and plus. It's going to recognize them in what is called its global rule base. The global rule base is the set of all rules that Mathematica know about how to manipulate M expressions, how to evaluate them. So if I do that, I find that Mathematica evaluates the expression to what it should be, which is 3 plus 4 is 7. 7 times 4 is 28. And if I try to do this within tree form, I get just 28. So what is happening here? Why isn't tree form showing me, the tree that shows times 4 and then plus 3, 4 that I got before? Well, what happens is that Mathematica does what's called eager evaluation, right? Whenever it sees an expression or a sub-expression that it knows how to evaluate, it evaluates it on the spot. So here tree form, with the Mathematica evaluator sees tree form, and then before it even applies tree form, before it even evaluates tree form, it evaluates everything inside the tree form. So it goes in and sees the times. Before it even evaluates it, it goes inside and sees the 4, and then it sees the plus, right? And then finally it reaches the plus, which is at the leaf end, and it evaluates it to 7, and then it evaluates the time to 20 times to 28, and then it evaluates tree form. So this sort of evaluation is called applicative order or eager evaluation. So if I put in 2 again and 2 again to get back the tree structure, Mathematica always evaluates from the bottom, from the leaf. Those, by the way, 4, 3, and 4 are called the leaves of the tree structure, right? So Mathematica always evaluates from the leaves upwards. So that's called, again, as I said, applicative order evaluations. So it sees times, and then it sees 4 and then plus, and before it does any multiplication, it evaluates plus, which when it looks at its arguments, those are atomic arguments, so it doesn't have to do any more traversing of the tree. So it evaluates the plus first, the inner portion first, and then it evaluates the times, which is naturally what would happen in mathematics anyway, but it follows that rule for everything. So formally, how does the Mathematica evaluator work? Evaluation is the act of checking an expression against the global rule base, essentially a list of substitution rules. The rule base is a huge list of substitution rules of the form E maps to E replacement. E is any M expression, and E replacement is any E expression. Remember, numbers, strings, or any other atoms are also M expressions. So the evaluator, when it encounters an expression, it searches for it in the global rule base, and then substitutes it with the replacement. Mathematica has also a fixed point evaluators, which means that after it does the above replacement, it rechecks the rule base to see if there is any rule for E replacement and then applies that. So it finds an expression, it searches in the rule base. If it finds the rule, it replaces it, it does a substitution, and then it looks at the result and then does another search through the rule base until it finds it again and then does the other substitution. It keeps repeating and repeating, doing that again and again until the expression reaches its simplest form, reaches a form that doesn't exist in the rule base anymore, and there are no more rules to apply. The other thing is that Mathematica has an applicative order evaluator. Well, mostly. But what does an applicative order evaluator mean? Well, it means that it evaluates the head, then all the arguments fully before applying the head to the arguments. I say mostly here because some heads carry exceptions and the evaluation order can be controlled in sometimes complicated ways. But for the majority of expressions, applicative order holds. For example, if we have something like foo, and then inside it there is +1, 1, and then +3, 4, this thing evaluates the arguments first, +1, 2, and +3, 4 completely. So the inner two plus functions are evaluated completely, then the results are passed into foo. That doesn't have to be the case if it's not applicative order, because there are some evaluators out there, like Haskell, for example, that are normal order, or what's called lazy evaluation, where plus the whole thing, +1, 2 is passed into foo, and then +3, 4 is also passed into foo, and then only if inside the body of foo or inside the definition of foo, +1, 2 is needed, or +3, 4 is needed, only then it will be evaluated, not before. That is typically called normal order or lazy evaluation, but Mathematica mostly is not like that. Mathematica is similar to Lisp in that it does eager evaluation or what is called applicative order evaluation. The arguments are completely evaluated first, and then they are passed to foo in this case. So we established that everything is an M expression in Mathematica. When I say everything, I mean everything. That can get very annoying with all the parentheses. However, I personally don't mind, because for example, Lisp has a lot of parentheses, and that's part of the syntax, and I never minded that. You get used to that after a while. However, many people don't like all the parentheses everywhere. And if you have complicated M expressions with many sub-expressions inside them, you might end up with tons of parentheses. So Mathematica offers syntactic sugar, where some expressions can be typed in non-M expression form, but before they go into the evaluator, they are automatically converted into M expression form. This is the part of the transformation that we talked about earlier. This is one way that transformation happens before we go into the evaluator. An example is, for example, instead of writing +3 +4, Shift Enter, right? I could write just 3 +4 this way. I can write it this way and press Shift Enter, and Mathematica is still going to understand it. It will convert it as +3 +4 in this form as an M expression, and then it's going to evaluate it. Something a little bit more complicated that involves also multiplication. So we could have 3 times 4 plus 5 times 6. By the way, when I enter the syntactic sugar, I don't need to have the multiply. I can just leave a space. When I leave a space, Mathematica understands it as a multiply. I'm not sure it even understands the star sign as multiply, but let me double check. Oh, it seems it does. Okay. So if I leave space, it understands it as multiply and gives me the result 42. By the way, that was an accident. I wasn't expecting to get 42 there. All right. So what is this syntactic sugar for? Let's say I could figure exactly what is the M expression here, right? But what if I have some syntactic sugar and I know that it turns into an M expression, and to be sure what my code is doing, this is a simple example, of course, but for a more complicated scenario, to be sure what the code is doing, sometimes you want to look at a piece of code that's written in sugar form and then get the actual M expression that goes into the evaluator. So to do that, there's a primitive form that is defined by Mathematica in the global rule base. It's one of the primitives of the system, and it's called full form, right? So if I say full form, and I take this and press Shift Enter. Oh, well, that's not very helpful. Why is that not very helpful? Because remember what we talked about, applicative order evaluation. So Mathematica evaluates the argument before it applies it to the head, right? So this whole thing, 3 times 4 plus 5 times 6, gets evaluated into 42 before it goes into the head. So how can we avoid that? Well, remember when I said that although Mathematica is in general applicative order, we still can in many ways sometimes control the evaluation mechanism. Well, one other primitive provided by Mathematica is called hold. So I could say hold and then brackets. What hold does is whatever M expression inside the hold is not evaluated. It's frozen. It does not get evaluated. It gets passed as is. So now I can apply this to full form. And when I do that, I see what 3 times 4 plus 5 times 6 in sugar form or syntactic sugar form is equivalent in real M expression form. I see this is equivalent to plus. And then inside the plus, there are 2 arguments. The first argument is times 3 times 4, and then times 5, 6. So this is how you can have a sugared expression and figure out exactly what it looks like before it goes into the evaluator. That sometimes can be very helpful when debugging or very helpful when trying to understand some format that you see that you know is syntactic sugar. Anything that in Mathematica that is not an M expression is syntactic sugar, developed just to or given to you as an option just to make your code more readable. M expressions and their counterpart in Lisp S expressions are really famous at potentially giving you code that is really hard to read. All right, but this is the point of having this sort of syntactic sugar. The way to find out all the different syntactic sugar forms in Mathematica is to look through examples and look through the documentation. There's no point of listing them all. There are so many. However, when we go through examples, whenever we encounter a form, I will explain it. And whenever you code, and that's the best way to learn any programming language. Keep coding and coding and coding in it, and do tons of examples. So whenever you go through examples, you encounter many forms and you learn them along the way. So I will highlight them as we go along, rather than listing them all right now. Okay, now let's move to the means of abstraction. The main means of abstraction in Mathematica is to take all those complicated expressions that we might build, M expressions, and then bind them to some symbol, right? So it's the act of taking symbols and binding values to them. That then we can take that complicated thing and just refer to it using that symbol. That's a very common mechanism, and that's the main way of dealing with expressions in Mathematica, because ultimately what we want to do is we said we are working around with a background of a global rule base. So we have whatever number of primitive rules that are part of the Mathematica system, and the act of programming for us is going to be, okay, we want to write programs that essentially add to that rule base, so that we can, when we run our programs, we don't only refer to the primitive rules that already exist. We want to build our own rules, right? That we can apply to our code. That is the main mode of abstraction. adding to the rules that already exists. So the main mechanism of doing that is binding symbols, right? That's the first way of doing that. So when binding to the symbol itself, there are two things we can do. I'm going to start with the first thing we can do. When binding to the symbol itself, let's say I have a symbol X, we are essentially adding a rule for it in what's called the own values of the global rule base. What do I mean by that? So let's give an example, right? So let's say I want to bind something to the own values bin of the symbol X, right? So first, there's a Mathematica primitive called clear. I don't want to deal with the issue that X might have been predefined somewhere by someone or by yourself while you're coding previously. So I want to start fresh. So I say clear X. By the way, be careful. Don't use clear on something that's already part of the primitives in Mathematica, because it will clear it unless it's protected. Well, let me try. I don't know. I don't remember. So if I try to, for example, cosine is a primitive. So cosine 3.0 gives me a value. Can I clear cosine? Yeah, it's protected. Yeah, so you cannot mess it up. However, sometimes if you have a complicated program, you have to be careful that you don't clear something you already wrote yourself unless you intend to clear it. Anyway, so I want to clear X just in case it was defined previously somewhere while I was experimenting. So I'm starting with a clean slate. And then what I want to do is I want to set 5 plus 6 to X. I want to bind X to 5 plus 6. So this equal sign means set, essentially, right? So this, by the way, this is the syntax for comments in Mathematica, parentheses and star. I can type anything inside as a comment. It will not be evaluated, right? So this binds 5 plus 6 to X in the own values bin. If I press Shift Enter, I see it evaluates to 11, but now X is bound to 11. Whenever I evaluate X, the evaluator sees the symbol X. The first thing it does, it checks, does it have a rule somewhere in the global rule base, right? If it doesn't, it evaluates to itself. It spits out X, right? For example, Y doesn't have a rule, so Y spits out Y. However, X has a rule, spits out 11, right? So the first place in the rule base, it looks through what's called the own values, right? So if I go to own values, this is again a Mathematica primitive. Let's say Z. Oh, I defined Z previously by something. Let me use something I haven't defined before. Y, yeah, it's empty. However, if I do X, it shows that it has a rule inside the own values bin that says if you encounter X, ignore the hold pattern. Hold pattern means this is a pattern that's not to be evaluated. This is just to compare against, right? So if you see X, substitute 11 or evaluate to 11 or replace it by 11. So this is what's called the term rewrite rule. Whenever you see X, change it to 11. We say 11 is the own value of X. By the way, again, remember when I told you that everything is an M expression? Well, here we have something that doesn't look like an M expression. What can we do to figure out what this is? Well, we can always desugar it, right? I can copy this. Then I can say, what can I say? I can say full form. Shift Enter, and I desugar this. So this whole thing in M expression form is list, because those brackets, those curly brackets, are syntactic sugar for lists in Mathematica. So lists are just a way of grouping data in Mathematica that is, well, it's a special way of grouping them because there are special functions that handle lists. So sometimes it's useful to group things as lists because then we can use the special functions that handle lists. But it all is at the end just a bunch of M expressions, right? So those curly brackets are syntactic sugar for lists. And then I see this thing here, the arrow with the two dots, is what's called rule delayed. This means that when you apply the rule, whatever on the right side of the rule, don't evaluate it. Evaluate it only when you see the X, right? And then this is the pattern that you're comparing against, and this is what you're substituting it with. Also, I haven't shown you what the actual form of this is, the set function. Essentially the desugared form of it. So we can do that right now. So I can say full form and then hold so that it's not evaluated, and then copy it and put it in there. If I do a shift enter, yeah, I see the full form of it. So it's what's called the set command or the set function or the set symbol. Right? So it's a primitive in Mathematica. It essentially does this whole thing of creating the rule in the own values bin. So the other thing we could do is we could bind symbols with set delayed instead of set. So this equal sign here represents set. We could do something called set delayed. It's the same as set, but with one major difference. We are binding the symbol to a right-hand side. So the binding has a left-hand side and a right-hand side. The left-hand side is the symbol we're binding to. The right-hand side is what the symbol is pointing to. Set evaluates the right-hand side always before it binds it to X. We could choose a different behavior. We could want sometimes to have, actually it's more common to want to have this behavior where we don't evaluate the right-hand side. We only evaluate it when X is used or X is called in an expression, right? So let me show you how that works. So if I go back here and say clear X to make sure X is cleared, and then I say X set delayed. Set delayed is represented by a colon and then the equal sign. And then I do 5 plus 6, and then shift enter. Previously, I got 11 because 5 plus 6 was evaluated. Here I get nothing because 5 and plus 6 is not evaluated. Now if I go to own values, X, so you can see the whole pattern has X, and then with the rule that it goes to 5 plus 6. Notice that previously the rule evaluated 5 plus 6 to 11. Here in this case, it was not evaluated. It is delayed essentially. This 5 plus 6 is only going to be evaluated whenever I call X or I use X in an expression. So if I say X, it will go to the rule base and to the own values set or bin, and it's going to look for X, and then it's going to see on the right hand side there's 5 plus 6, and it's going to evaluate 5 plus 6 and give me back 11. I could say X, Y. I can build an M expression. When I do then shift enter, I get 11Y. I mean, that doesn't mean anything. It's just an M expression. An M expression doesn't always have to have a meaning. You decide what it means, right? This is a valid M expression. And it sees that there's an X there, so it decides to substitute that X with 11. So we have an M expression at the output that has a head of 11. Let me desugar this. So that's just to show you how it looks. Full form. It gave me null. Why did it give me null? Well, see, the thing is, everything is an M expression. So this thing evaluates. Not everything evaluates into something that's a number or a result. Sometimes things evaluate to nothing, and we represent that by null. So although this thing has a side effect, which is adding something to the global rule base, to the own values, adding this, right? It still evaluates, right, to something, and this something is null. Previously, x equal evaluated to 11 because this is not set delayed, this is just set. So the right hand side evaluates. So its behavior is that it spits out the whatever the right hand side is. However, the set delayed's behavior is that it spits out null when it evaluates, but it has a side effect of adding this pattern to the rule base. So to get this correctly, the full form correctly, I need to do a hold, so that whatever is inside the full form does not evaluate. And I see here the full form or the desugared form of this expression. This is set delayed x plus 5, 6. And then all the, oh, by the way, I've been calling those parentheses previously. Those are not parentheses, those are square brackets. Parentheses are those symbols, which are common in Lisp. This is what's used in Lisp. While in Mathematica, we use square brackets and curly brackets for lists. We can also bind to symbols when they are the heads of M expressions. In that case, the rule goes into what's called the down values list of the global rule base, right? So let me clear x, and yeah, so what happens is that whenever x is not just x by itself, it's part of an M expression. Let's say y w, right? That's an M expression. So whenever I have it in a set expression where I'm trying, it's in the left hand side of a set, right? So I'm trying to apply a rule to it. I'm trying to bind it to something. So let's say I bind it to a, or a might be, I might have defined. Actually, let me clear both y and a, just to make sure that they are not defined previously, right? So when I do that, this expression evaluates to a, as we are used, as we understand right now, because this is a set, this is not a set delayed. So the whole thing evaluates to the right hand side. However, when I look now at the global rule base, previously I used to look at the own values, right? If I look at the own values of x, there'll be nothing, right? Because here this is an expression, this is not just x by itself. However, if I look at the what's called the down values of x, I see the pattern here. I see the M expression where x is the head and the whole expression is bound to a, right? So that if I type in x by itself, nothing happens because x doesn't have an own value. Whenever you evaluate expressions, whenever Mathematica evaluates expressions, the first thing it does is that it looks at the own values list. If it finds an own values, it substitutes it instead of x. If it doesn't, and x is the head of an expression or the head of a sub-expression, it then looks at the down values of x, and it finds a pattern, and it gives it to me. Right, so if I have x, let's say wy, nothing happens because the pattern is xyw, right? So if I put in xyw, it finds that and it gives me a. Can an expression have both an own value and a down value? Yes, it can, but in that case, the own value will always supersede the down value. So let's say here I say x equals 4. X now is going to have an own value. So if I say own value x, oh, what's wrong? Oh, own values. Okay, values. Own values x. I see the pattern here. If I look at down values x, the down value is still there. However, the own value will have priority. So if I do again x, y, w, see the own value is applied first. So it sees this expression, it sees the x by itself, it checks the own values first, and it finds that x maps to 4, and it changes the expression to 4YW. And then there's nothing to do with the down values because the expression is lost now because X has changed to 4. It's typically not very elegant to mix down values and on values. It's typically preferable to either have symbols that have on values or symbols that have down values. It is very rarely appropriate to have symbols that have both. Sometimes that can be of use, but it's always preferable to just either use on values by themselves or down values by themselves. This kind of action where we take something that should be at the head of an expression and change its own value maybe can be applied sometimes if we have something like I don't know, Newton's method or some algorithm that takes in a function. So we could have a variable function or f, and we could change its own value to some other function. But even that, it's more elegant to do in other ways. I'm not sure 100% about what is the history. So I know how, I described how on values and down values work, but I'm not sure 100% about the history of their introduction. Why were they introduced to begin with? What was their philosophy? But I have a suspicion that it has to do with the demarcation between Lisp 1 and Lisp 2, because of course Mathematica is heavily influenced by Lisp. In Lisp 1, there's what's called unified namespace, meaning that functions and symbols share the same namespace, while in a Lisp 2, there's a separate namespace. So you find situations where you can have a name that is the same for a function and a variable, right? So I think that could be the influence, but I'm not sure. I want to discuss a bit grouping expressions. So typically when we write a program, the program will not be just one expression, it will be multiple expressions. So if I have, let's say, a equals 3, that's one expression, right? And then if I do b equals 5, x, y, w, and so those are 3 expressions. And notice I always pressed enter after I typed each expression. If I type shift enter, I get those 3 expressions evaluated in consecutively, right? So the result of this expression evaluation is 3, the result of this is 5, and the result of this is what we defined previously for YW, because we gave X an on value. Let me make this a set delayed to show you what will happen. If I do this, the null doesn't show, of course, because typically when a null is when the resultant is a null, it doesn't show. It's just suppressed. It's not printed unless I force it out by using the full form. Okay, and let me put it back. Now, whenever there's a list of expressions, what we could do, let's say when you write a program, you might write a list of expressions, but the output that you're interested in is just the last expression. So there's a way to suppress the output showing up, which is putting or placing a semicolon at the end, right? So when I do that, when there's a semicolon at the end, this suppresses the output of the evaluation on the first line and the second line, and then the third line, let's say I put a semicolon and I press shift enter, nothing shows up. But if I delete the semicolon and press shift enter, I get only the final result. Now this might be interesting to show is that this whole thing, this whole grouping of expressions in this way is also an expression. So you could collect smaller expressions to bigger expressions. Of course, here this is done with this sugar, the syntactic sugar of using the semicolon. I guess the best way to show this to you is to copy this. So if I go back to our trusty full form and I paste this, I could, by the way, have an expression that spans multiple lines. I don't need to have it all on one line. and I mean like multiple lines between the brackets. This is fully legal form, and sometimes this could be more readable than having everything between the brackets on a single line. But if I do this, of course I get 4YW, nothing changes. Why? Because I should have put what? I should have put hold. I should have held those expressions so that they are not evaluated. And I close the hold. So I'm using this multi-line style of I'm using this multi-line style of formatting between the square brackets. When I press Shift Enter, so you see this multi-line set of expressions is what's called a compound expression, and shows up when I try to print the full form. So set A3, set B5, and then X, Y, W collected together form a compound expression. And the way this is internally represented is by using the compound expression name, which you could use also, right? I could have done this. I could have said compound expression and then A, B, 4, and I will get only the last one. Only the last one is the result of this expression, but this is exactly equivalent, right, to the syntax sugar of A, B, and then 4, and then Shift Enter. So it is surprising sometimes when you think about it. It's surprising sometimes that things that you might not think are expressions are actually expressions. Everything in the point that I'm trying to drive, everything is an expression. And if you are in doubt, use the full form name. To check out what are the names that are defined by the system and have rules, well, what you could do is you could use the names function. So I could say names and then say search for all. So I give it a string of star, which means all, everything, and it will list everything in the system. And there's a lot of stuff in there, right? It's a huge amount of symbols that are defined and that that have their own rules. If we go scroll all the way down, I believe I'm trying to find the X that we defined. Right, if we scroll all the way down, we will find the X that we defined in our example. Here it is. So this is the X that we defined. Now let's say you want to count how many names are those. Well, there's a way to do that. I'll show you. So this is essentially what? This is essentially a list, right? So there is a function called length. So if I do this, what happens is that the names do not get printed out. The output of names gets passed into the function length, and then length just finds what is the number of elements in this list, and it's 7,963. There's something on Mathematica called context. So this is typically how it makes the organization of names more manageable, symbols more manageable. I'll discuss it later, not now. But if you want to more focus on what is defined in your session, you can say global dash, and just that shows you like a subset of everything that the system knows about. Let me go back to names and let me pick up something. Let me pick up, let's say, accumulate. So I could pick up accumulate, and this is like a system symbol. This is defined by the system. If I go all the way down and I do the same thing that I did before, which is check what is the own values of this system defined symbol, I see there's nothing. But does it have a down value? Let me check. Okay, it has also nothing. So whenever you find a symbol that doesn't have any own value or down value, that means that there's nothing about this that is implemented in Mathematica itself. This is probably some lower level primitive that is written in C. The underlying language underneath by Mathematica, in which the core is written in, is in C. So this was probably implemented in C and provided as a symbol. If you want to find help on what it does, you could always type the name, accumulate, and then it offers to take you to the help screen, right? So it tells you what it does exactly. Gives a list of the successive accumulated totals of elements in list. One final thing I want to mention is that there's a nice syntactic sugar for applying something to a result, right? So here I have names, right? And I wanted to apply length. So what I did is I did this, right? Then shift enter and I got the length. That form is what is called the prefix notation. There is, however, a form called postfix notation, and we do it by applying the syntactic sugar, the two double dashes, right? And then saying length. So this is equivalent to the form before. So if I type this or I type this, I get the same thing, right? I get the same result. This is sometimes a nice syntactic sugar because if you have a large expression, let's say, and you want to append some other symbol to it at the front, you don't have to go back and put in the square brackets. You can just tag it at the end like this. So if I take this, for example, just to prove to you that this is just syntactic sugar, we go back to not hold form, full form, right? And then I say hold, and I get the same thing. So this turns into length names, right? I could have done this differently. I could have said this, right? So it gives me the names, and then I wanna have tagged to the front length. So I do this, and then I can do this, hold. So it holds it. And then I can do this, which is full form, and I get the syntactic sugar of this. So this kind of sugar of using this postfix notation to get the same result as this prefix notation, which is the formal form of an M expression. This is the true form, by the way. Sorry. This is the true form, by the way. This is just a way to make our lives easier sometimes by just tacking something at the end and getting the same result. I wanted to get into patterns, but this video has already gone too long, so I'm going to leave discussing patterns for the next video. And I'm hoping to get into examples, because to really understand the language, you really have to do a lot of examples. And I'll try to do that. Thank you for listening up to this point, and I'll see you in the next video.